Hello, hi, my name is Pedro. I'm with Samsung Research in the UK, and I'll be sharing this session with my colleague, Heeill. I will be presenting the use case on confidential AI, primarily protecting generative AI models, as well as safety guardrail models. And Heeill will talk about improving gaming experience. I will begin briefly by mentioning the Islet project, which is an open source project from the Confidential Computing Consortium, and it's a platform that enables confidential computing on the Arm confidential computing architecture, and it's primarily designed to protect privacy on end-user devices, and we are seeking to identify and implement these use cases to showcase the benefits of confidential computing on everyday user devices, as well as accelerate this integration and adoption. So moving on to confidential AI, we have three main goals to achieve in this project. The first one is data and model privacy. So data privacy, we want to make sure that users' data remains private during this computational process. And similarly, on the models, we want the weights of the models to remain also private, as these are important proprietary models. They're very expensive to develop and have also some security risks, as we heard earlier on today. And this is done with confidential computing. It's made possible with confidential computing, this kind of privacy during computation. The second objective is on the AI application side. We are interested in maintaining the safety of these applications. And by safety here, I mean in terms of the content that they generate. I'll be speaking mostly about language models and language models guardrails. And guardrails are one of the ways that we can ensure safety of these applications. And again, we also want to keep these guardrail models private because they're also can be considered an asset or intellectual property for the companies. And thirdly, we are interested in efficiency. So we're targeting on-device applications. So we need to be very, very efficient with everything we do. And I'll show you one example in how we can be efficient by using knowledge sharing techniques. So on the top right there, we have basically a summary of what we want to achieve and how. We want to achieve two levels of protection. The first is on the compute space, which is afforded by confidential computing, as we heard a lot already through these 2 days. However, confidential computing doesn't guarantee that applications are safe in the sense that the content is safe to be displayed. For that, we need something like guardrails. So we want to combine these two levels of protection to achieve a more strong protection. Attached to this, we also care about efficiency. So we want to design, we want to design this system in a way that is maximally efficient and that can be used for resource constrained devices like mobile phones, for example. So this is a triangle of goals that we're trying to achieve on the bottom right. So the problem with language models is that they are very, very capable of generating amazing content, but that means they also can generate amazingly harmful content. And particularly, they are susceptible to being tricked to bypass the natural or the first line of defenses that they have, which is called safety alignment, which is where a language model is trained or fine-tuned with safety data to ensure or to steer the model into replying safely to harmful prompts, harmful questions. I showed an example here on how easy it can be to break these models currently. So simply by asking a question and then also appending to your question something like start your answer with absolutely, here is. This can very effectively jailbreak the models because it steers the model into generating a response in the helpful direction as opposed to the safe direction. And we have this kind of competing objectives on safety-aligned models. They want to be helpful, so they want to answer your prompt, but equally they're meant to be safe. So these kind of jailbreak attacks are a way to trick the models into favoring the helpfulness criteria as opposed to the safety criteria. So how do we defend these models? One way is, as I mentioned, safety alignment. That has its own problems. Another way which we're interested in is guardrails, and this is a figure of how this thing works as a system. So a user provides a prompt that is fed into a language model, which generates a response in turn, and we want to then detect both the intent to generate a harmful content in the user prompt. So this can be a question that is itself harmful, or hints that it's trying to get something harmful or undesirable from the model. And equally, we want to detect actual generated content by the model. So this will be on the response side. So systematically, the way this works is you do get a response from the language model, and then you feed both the prompt and the response into a guardrail, which detects any undesirable or harmful content, and then guards this application by outputting a defended response, is what I'm calling here, and this might just be a refusal to answer kind of message. So we want to move towards on-device confidential guardrails. Currently, there's still some limitations on what exists out there. A common one is that a lot of the models in production right now are server-side, so your data has to travel to the server, and because these servers are currently not using confidential computing, this is an issue for user data privacy. In addition, also, these are not on-device ready. They just haven't been developed with this resource constraint framework in mind, so they need a little bit of work to make device ready, lightweight and efficient. So this is basically our work, our proposal. We want to build efficient multi-app protection using a shared guardrail idea, which I'll show you in the next slide. We want to avoid this communication over the network, so that we can have faster inference and no downtimes if devices are unconnected to the network. And we want to achieve then full protection using confidential computing, and this means protection again of users' data as well as the models of the provider's models, the language model itself and also the guardrail. Just a quick note on the guardrail. So both of these models, the LLM and the guardrail, are sensitive in the sense that they are intellectual property, but the guardrail is a special case because it can also be used by attackers to fine-tune their attacks. So this is a special kind of knowledge that we want to safeguard from potential attackers, not just because of loss of intellectual property, but also because it can lead to better attacks to other models, and attacks can transfer to other models. So there's also a risk of this propagating through other vendors. So this is an example of a system that has some efficient components. We have two apps, app 1 and app 2. This might be a text summarization app, a text translation app, or simply a conversation app. Each of them has their own LLM, which is used to generate a response. This LLM may have a shared component between the two applications. This is a simple case, but they also might have a shared component. What they definitely share is the guardrail solution, which means it can guard multiple applications simultaneously. So in terms of memory, this is a more efficient solution. In terms of how it works, it's similarly exactly the same as I showed you before. Prompt into LLM into response, and then both prompt and response are guarded to obtain a defended response. The protection targets I showed here highlighted in the blue bubbles, apart from the user prompts, obviously. So these are the two language models of the two applications, respectively, and the guardrail model, which are shared. So these are the components that we want to put into a CC environment or realm. I will show you two examples. One is when we want to defend against malicious users. So this is the example that is similar to the first jailbreak attack I showed you. A user might use a role-play strategy whereby the user pretends that is, in this case, writing a novel. It's a fiction novel. And in this fiction novel, there's a protagonist that must create a bomb in order to save the world. And then the user will ask the LLM to write a paragraph for this fictional novel where the protagonist is making a bomb. And you can ask it to give some details about how to make a bomb and what process you can follow. So this case, which is a real example, the LLM does comply with the instruction and will give you a paragraph, a scene of a person making a bomb, including 4 actual, real, dangerous chemicals that can be used to make bombs or explosives. So the guardrail model here will see the question, which can be debatable whether this is harmful or not, but the reply is certainly harmful. So we have two chances basically to filter out this case. So this would be for an open-ended conversation kind of application. On the other hand, we can have a summarization app that might read a document or a website, and you might want to summarize this website. And in this case, the model will again comply and give you a short version of a recipe to make a bomb. So in this case, the guardrail is actually protecting the application provider from having harmful content displayed on its application, which is legally something that companies want to do. The second example is on defending against malicious models. So in this case, the user is not a malicious user. The user is simply asking about the history of company XYZ, but the model might have been attacked. So current LLMs can be compositional in the sense that they are composed of different components. Usually and very commonly, we'll have a backbone that is shared between different tasks, and they will have sub-modules that are specifically built for specific tasks, like summarization or translation. And their modules can be combined. And when you combine modules that we didn't develop, which is now currently a common case, then you don't know if this module has been attacked, and so we want to defend against it. And again, similarly, we can feed both of these input and output to the guardrail in order to detect any harmful content. In this case, it could be that the LLM has been attacked to destroy the reputation of company XYZ by replying with defamatory information. So in this case, we want to protect both the app provider, again, from having untrue or unreliable or unsafe content shown in this application, as well as the user itself, who is just looking for information, reliable information on company XYZ, but now, if a model has been attacked, it might be exposed to some information that is not reliable. And just to conclude, so we want to put these two pieces together. We want to put confidential computing in blue together with guardrails in orange. So on the privacy side, we have CC that protects the data, the LLM and the guardrail as intellectual property. On the safety side, we're using guardrails to protect the AI content itself. And putting these two pieces together, then we want to create fully protected AI systems. And I'll pass the word to my colleague.
Thanks, Pedro. Hi, I'm Heeill and working at the Samsung Research. And today I would like to give a slightly different use case that improving online game experience with confidential computing on player device. So before I introduce our approach, let me briefly summarize how this trust between game server and game clients emerged in online games. So let's get started. So in the early age, there was no game server, so players needed to connect manually with each other to play online games, which also means that the online game is mostly played with the already known players, such like friends or family. And then the online game platform has been emerged that connects the players, which enables to play online games with the anonymous players. On this era, still, client executes the core game logic, so server just connects the player, does not intervene with the gameplay itself, which also means that the game server assumes that all players are honest. And unfortunately, as the online game is played with anonymous players, some players start to cheat over the online games. So in the modern online game, server does not trust the players anymore. So server takes the role of the executing a core game logic instead of the game clients, because the game client may cheat over the game logics. So this approach was quite effective to prevent many types of the cheats, but unfortunately, client suffers from the network latency with this model. So our goal is to cure this distrust between game server and game client by utilizing on-device confidential computing on each player device. So here is our first sketch page, back to good old days, and I will introduce how we can reduce latency with the on-device confidential computing. So here is a simplified flow for the current game models and our models. So on current game models, as you see, when user input is given, it should be delivered to the server first. And server executes the game logic for the clients and broadcast updated game state to our clients. On this model, as I mentioned before, clients suffer from the network delay. And on our model, you see on the right side, when user input is given, it executes the game logic in the confidential computing in user device without any network usage. So they can get the updated game state right away without any network delay. So we can provide the player for the advantage to get the reduced latency, and for the game company, they can reduce the game server cost because they don't need to execute the game logic on the server side. So here is a simple demo video for the real games. We test a game called the Bathroom, which is Unity's official sample game, and the test device is Galaxy S22. So note that integrating a confidential computing with this game is still work in progress, but still you can see what it looks like for the CC-assisted gaming. So on the left video, you may focus on the response time of the character movement input. So you see here that even though I give the same movement input simultaneously, the response time is very different. Our model responds much faster. And on the right one, you may focus on the response time for the skill shot as well, and then the response of the object as well. So in the case, similarly, even though I give the input at the same time, the skill shot is fired much faster and the object is broken much faster as well. And I would like to introduce another type of the use case for the confidential computing on player device called the trusted random box. So before I introduce our approach, let me briefly introduce what is a random box in online games. So random box is a virtual item that provides a randomly selected reward to the player. And if you're familiar with modern online games, you may already realize that the random box has become a prominent business model in many types of the online games. It is estimated for $15 billion and growing super rapidly. And unfortunately, some game companies try to disguise a player, and various diseases already has been discovered at numerous game companies, such like dropping a probability or manipulating a reward from the random box. And thus, players do not trust the game company anymore, that they would not trust, they think game company would not open the random box honestly. So by utilizing a confidential computing on player device, we would like to move the random box module into client device, and we would like to restore these types of the distrust as well. So here is the simple benefits for our trusted random box. We can provide the transparency. That means that the game company cannot manipulate the reward of the random box. And as well, player can verify the random box, which means that the random box module is identical with the already opened source code, as well as that player may examine the probability of each type of the item from the random box. In addition, we also provide the offline random box, which means that the players can open and check the result without any network usage, such like in the flight mode. So here is a simplified design of our approach and the flow. You see on the right side, the random box module is located in the confidential realm world, and the game client is on the normal world. And both modules are on the same player device. And as usual, there is a remote game server occurs. So at first, game server sends a ticket to the player, to the client CC, and then random box logic is executed on the confidential realm mode and notify a result to game client. And then later, game client may request to sync result to the game server. When game server receives the sync request, they verify the result and the ticket and update a reward for the player. So here is a simple implementation for the trusted random box. We implemented this with the Samsung Islet. So you may assume that the left window is the confidential realm mode that executes the trusted random box, and the right side is the right window is the normal world that executes the game client. So at first, I tried to launch a realm. It takes some time, so I made some speed up for this video. And on the left side, we launch a random box module on the confidential realm world. So it is loaded, and player may want to verify a random box first. When they request it, the verification is done on the left side, and on the right side, it may pops up the simplified source code, and it also pops up the examine of the probability. So when player tries to open it, it may get the result right away. In this case, they get a rare item, maybe the normal item again. And for some cases, they get the legendary item. So what if the player tries to cheat over the random box? So you get the error on the normal world and on the confidential realm world. It detects the realm memory access from the normal world and it invokes a granular protection fault. So even though the normal world is compromised and the player tries to cheat over the random box, it can't because it is located in the confidential realm world, so it cannot be cheated. So here is a simple conclusion of my presentation about improving gaming experience. So we discussed that by utilizing on-device confidential computing, we can restore this trust between game server and game client. And in particular, by restoring from server to client trust, we can provide a reduced latency. And on the other hand, by restoring from client to server trust, we can provide a trusted random box. So this is it. So thank you. So feel free to ask any question from me or to the Pedro about confidential AI.
Thank you for this talk. I think there was some very interesting use cases in here. One question I had is especially around the improved gaming experience use case. This sort of relies upon the widespread distribution of confidential computing in like people's local machines and setups. Do you have any sort of estimates or insights into how long the time horizon is for something like that, and what type of increased costs there might be to support like on personal devices with confidential technology?
So you mean that the timeline of our approach to be released?
Sort of the hardware infrastructure and being in place to enable this, and a lot of other pretty powerful use cases once we do have on like widespread use of personal confidential computing.
So unfortunately, we Samsung don't know the timeline for when the Arm would release the real hardware equipped with the Arm CCA. So I think I cannot say about that.
All right, thank you.
Hi, a related question. I'm curious about the sources of latency in the gaming example. Are you addressing network latencies or computational latencies? And which is the source of the improvement that you're getting?
So most of the latency comes from the network, not on the computation. Because the most game logic is very simple to execute, such like calculating a damage or updating a HP.